Greetings, everyone. You are at the right place for the USAPhO webinar, and we're going to wait for maybe 1 or 2 minutes till all the registrants are come in, and then we're just going to go ahead and start. Okay. Okay, welcome to the USAPhO webinar, and thank you for taking the time at very challenging times. So I am JJ Dong. I'm the academic director of the US Physics Team program. Today with us, we have 3 coaches joining us, and then go over some of the questions from this year's USAPhO. So let me briefly introduce them. So we have I don't know how the screen orientation are, so I cannot even point you to the specific picture, but I think you can see their names at the lower left corner. So we have Kai Shi, who is currently an undergraduate student at Mott College, and he's the gold medalist in USAPhO 2017, and he has been a coach for the US Physics team since 2019. And then we have Professor Brian Skinner. Hello. He is a faculty member at the physics department at the Ohio State University. He has been a coach since 2019. And then we have Dr. Mark Eichenlaub. He is a curriculum developer at the company Art of Problem Solving, and he has been a coach for the US Physics team since 2016. And the format of today's webinar will be the following. Each of us are going to take a few minutes, 5 to 7 minutes, going over the problems that you have worked hard on yesterday on the USAPhO this year. And the reason why we decided to keep hosting the USAPhO, even though we are not selecting a team, is because we understand you have all been studying hard and wanting to practice your physics skills. So we're going to take the time to, and since you've already seen the solution, what we're going to do is not, go into the details of the solution, but rather point you to a few of the interesting and intricacies of these problems. And hopefully that will pique your interest, and you can keep working on the similar types of problem and similar types of phenomena, maybe even go a little bit deeper at your own time. And so after the 5 to 7 minute brief recap of the problems, we're gonna open it to quick Q&A sessions on the specific problems. So you're able to submit your questions via the Q&A box. So if you can take a quick second, locate the button says Q&A on your Zoom box. This is where you will be able to get to submit your questions. And one of us will be able to pick up the question and answer you. And then we're going to move on to the different questions. Once we finish recapping this year's USAPhO, we're going to open it up and talk a little bit about general physics studying strategies, and also how we can help you to be better at learning physics, and how to encourage more students like you to participate in not only studying physics, but competing at the international stage. Now, speaking of the international stage, the organizers of the International Physics Olympiad of Lithuania has just announced today that due to the COVID-19 situation, they have decided that they will not be hosting USAPhO this July. And they will make a formal announcement concerning when and whether they will still host USAPhO this year on May 15th. So this is the most updated information that we have had. So I'm sure this will come as a slight disappointment to many of you. However, what I want to emphasize is in this, this is a physics learning community. And what we hope is USAPhO is not the only goal, but rather a part of the joy along which we are all taking and sharing together. Okay? All right, without further ado, I'm gonna lead off with going over the problems that we had yesterday from USAPhO. So I will go over question A1 and A2 with you. So let's go ahead and get started. Some of you have already mentioned that question A1. So question A1 is actually inspired by the famous Feynman's paradox. So what I will share with you is a link from the Fineman lecture notes, and you can go back to the notes in the link. So I just shared with you the link in the chat box. So if you can go to the chat box, you will be able to see it. And so it is a paradox that was not initially raised by Feynman. Many people have asked the similar question, and Feynman, of course, famously reformulated in his widely studied lecture notes. And in there, he raised the question without specifically answering it. So we actually formalized it into this problem, which in my opinion is not a particularly challenging problem physics technique-wise, but conceptually point to a few interesting phenomena. And I noticed some of you are true physics scouters and pointing out that it's very similar to the India Physics Olympiad 2020. So it's a very well-known physics paradox. So I hope when you're solving it, not only did you know whether you get to the right answer or not, but also notice the interesting physics involved. So what is the interesting physics involved in this particular question? Well, I hope the setup is fairly clear. You have a linear charge in the z direction, and then there is a it's a cylinder concentric to the line charge and with the opposite charge type distributed along it. And then this whole thing is set up in a magnetic field. So the relevant physics you need to use is basically Maxwell's equations, Faraday's law and Ampere's law, to figure out the relevant angular speed involved in there, okay? So there is a slight mistake in the equation 1-7 and 1-8. So when you are using the Ampere's law to figure out the induced magnetic field, the enclosed current, instead of being this lambda divided by 2 pi a omega a, there is an additional 1/2 pi factor that is not necessary. So the correct answer should have one fewer 2 pi factor in there. So basically the enclosed current per unit length should be the charge distribution divided by the period, and the period is 2 pi over omega. So apologize for that. Yes, so here the confounding issue is by the time the magnetic field, the external magnetic field is reduced to 0, there is still a magnetic field caused by the induced, Faraday's law and the induced magnetic field. And that allows you to calculate the final angular speed. And noticing that this whole system started from at rest, but wind up with an angular speed, that is where the paradox comes in. So in the eye of angular momentum conservation, it would appear that the before and after angular momentum is not the same. However, this is where part B comes in, and we actually caution you and point it out to you that this is, if you only look at the mechanical angular momentum, then there is some problem. So this is one of the examples where, you know, we're trying to teach you something by solving a problem. And in this case, we're trying to teach you about the angular momentum carried by an electromagnetic field. And if you go through the mathematics and compare the coefficients carefully, you will realize that the alpha sitting in front of this p vector, which is formerly known as the Poynting vector, and that is the energy density of an electromagnetic field, okay? So overall, this problem uses the Maxwell equations, and you need to practice and be familiar with working with within a cylindrical coordinate system, okay? So that is U1. Apologize for the extra 2 pi typo, and many of you were able to figure it out, so that's excellent. I'll leave it for 1 or 2 minutes questions concerning this problem before I move on to A2, swoosh.
JJ, you do have a question about whether you should use circular or square Amperian loops when you're analyzing this.
Amperian loop. In this case, okay, so if you're referring to solving the parts where you were trying to find out the induced magnetic field, in this case, the induced magnetic field is caused by the, so if you put yourself in the reference frame of the rotating cylinder, then what is changing is the line charge, right? So in the view of the line charge, that is the charge that's moving. So in choosing the Amperian loop, you want to choose an Amperian loop that encloses that part of the current. So, and then on the left-hand side of the equation, you are doing the line integral between the induced field and the line element. So if you choose a circular Amperian loop, then everywhere along this loop, the magnetic field will be parallel to the line element. I'm not sure how that will work out if you use a square Amperian loop in this case. So it's not, you're not using the nice symmetry created by the cylinder in there. Oh, by the way, I do want to mention that this webinar is indeed recorded, and the final recording will be posted on AAPT website so that we're aware that some of you still have high school classes, or you may want to review the information that we discussed today. So you will have access to this video afterwards. Okay. So yeah, that one is answered. All right. Next, let me move on to the second question. So this question, swoosh, is came from the contribution of Professor Emil Ariel. He is a professor at Harvard University, and he was a physics Olympiad competitor representing Team Israel some time ago when he was a high school student. So it was really a privilege to get contribution from him. And this is also sort of inspiring you to go on to pursue a physics career and come back and give back to the physics learning community. So this problem is a typical mechanics problem, but what is a little bit more interesting is this problem cautions you to look at the perspective from an inertial frame versus a non-inertial frame. And I've already seen in some of the earlier questions typed up today in the Q&A box, some students were asking, oh, is John and Ella's solution flipped? Well, to answer that question, you need to confirm who is an inertial observer and who is in a non-inertial frame, right? So to get you a little bit more interested in this Foucault pendulum, there is actually a very well-written article with a lot of details in the setup of the Foucault pendulum. And again, I am sharing the link of an article with you in the chat box. So this is something, again, you can read afterwards and get a little bit more things in there. And similar to the previous problem, in this case, we're giving you a very common physics phenomenon and just encourage you to think a little bit more carefully about the details in there. So in the case of John, he is in an inertial frame, watching the Earth rotating, right? So you set up the Newton's second law equation that will give you the answer to part A and B. And also, if you look at the solution, you will notice that in John's frame, the X and Y traces out a ellipse in there. And when we shift our perspective in Ella's frame, who is co-moving with the Earth, this is when you have a observer in a non-inertial frame. And this is when you have to consider all the fictitious force. And in this case, since Ella is at the North Pole, the relevant fictitious force here is the Coriolis Force. And you can either, so as suggested in the solution, you can either take the derivatives of the x tilde, y tilde expression and get the results. Or if some of you are more familiar with doing a reference frame transformation through matrix products, you can multiply it by a rotational matrix as well. So either way should give you the right answer. And the last part of this problem explicitly calls out the effect of a Coriolis force. And to figure out the period, or rather in this case, there's a slight distinction. What we're not talking about is how long it takes the plane of rotation to go around in full cycle, but rather we just say when will the plane return to its original point. So in this case, the time it takes is half of the entire plane rotation period, which is why it's not the familiar, 23 hours, 56 minutes, but rather a little bit less than that, half of that. But if you answer, it's, if it is 24 minutes, namely how long does it take for the entire plane to go back to its original place, that's very close to the final correct answer as well. So, okay, that is actually all I want to say. I want to also mention you may not be able to get a lot of practice on these, on the problems involving non-inertial frames. So a good reference or a good resource to practice a little bit more is David Morin's mechanics book. And in chapter 11, he specifically had a whole chapter on all the right. Okay, some students always also mentioning that too. So in Morin's chapter 10, chapter 11, he specifically talked about how to work out these things in non-inertial frames. And I believe the Foucault pendulum was also one of the examples used because it is a very nice experiment, and it also shows a lot of interesting theoretical phenomena. Okay, so all right. That's all I'm going to say about the second problem. I believe the solution is fairly self-explanatory. So are there any particular questions? Oh, some students were asking why the first problem is called breaking up. It's not really breaking. The cylinder is not stopping, but rather rotating. And we sometimes make these problems with a name so that it's easier for us to refer to, because the ordering of the problems change as we make the test. And I hope you will enjoy these names. Sometimes we work really hard to come up with the names. So, all right. I'm gonna pass it on to Mark then. I believe you're going over A3 and B1.
All right, hi everyone, I'm Mark. I think what I will do is I will just screen share with you so we can look at the problem as we go. And so There we go. All right, so now you should see the problem on the relativity problem should be up on your screen. And so what we have here is someone going around in a circle, which could be a little bit new to you if you've studied relativity before, because often we're looking at people moving in straight lines in relativity, not people going in circles. So you've probably seen a diagram like this one, where you imagine two reference frames, and we have one frame S and one frame S prime, and frame S prime is moving to the right at speed v, and that's called standard configuration. And so if you have sort of like memorized some equations for the Lorentz transformations or something like that, you've probably memorized equations for a situation like this. But we have a slightly different situation here, which is we have someone going in a circle. And so that does something a bit tricky, which is that this person going in a circle is not in an inertial reference frame. There's interesting ways that we can see that. One way we can see that is we can talk about part A. So in part A, we're just asked basically how long does it take Carla on Carla's stopwatch each time that she goes in a circle. Well, the simple answer is to use time dilation. So you can figure out how much time it takes her to go around in a circle from the lab frame, which is just the distance around the edge of the circle divided by the speed that she's going, and then say, well, due to time dilation, there's going to be a factor of gamma. Her watch is going to be going a factor of gamma slow. And that's the right answer. And that's valid because all of that analysis happens in an inertial frame, in the frame of the lab. But what if you were in Carla's perspective? So you're just riding along with Carla. Then what you would see is you would see the center of the circle going in a circle around you in the opposite direction. And in fact, the whole universe, right? All the distant stars and everything would also be going in a circle in the wrong direction. And if you take that point of view, you might think, oh, well, actually it's the clock at the center that should be experiencing time dilation. And there doesn't seem to be any like consensus answer into physics as to why Carla is the one whose stop runs slow and the one at the center of the circle has a clock that runs faster compared to Carla's, except that Carla is accelerating. And so it appears that the universe just has an absolute reference frame in which it says, this is an inertial frame. All frames moving at constant speed relative to are inertial, but frames that are accelerating relative to this particular one are not inertial. And so you can look at the distant stars as a way to see that. Because Carla sees the distant stars spinning around and someone at the center of the circle does not see the distant stars spinning around, we can say that Carla is the one who's really moving. And time dilation says that Carla's stopwatch moves less than the one at the center of the circle. But it leads to lots of really interesting paradoxes too. So if you think about how fast Carla's going, and then you say, how long does it take Carla to go around in a circle on her watch? And then from that, calculate the size of the circle that she's going around. So how big does Carla think the circle is? Well, Carla doesn't think the circle is 2 pi r around. She thinks it's 2 pi r divided by gamma around. On the other hand, if we look at this distance here, r, because that's perpendicular to Carla's motion, there's no length contraction there. So Carla thinks that she's going around in a circle of radius r, and that the distance around the circle is 2 pi r divided by gamma. In other words, it's not really a circle anymore, right? The circumference is not 2 pi r. And so that's something that's called Ehrenfest's paradox, if you want to look into that. Ehrenfest paradox. So the circular motion in relativity can be quite tricky. And in this problem, it turns out that it's not very tricky for A, B, and C. But then all of a sudden it becomes rather tricky for part D. So Carla's going around. We know from time dilation that we just divide by a factor of gamma in part A. In part B, we have a clock here and a clock here, and Carla synchronizes them. And so because Carla does the synchronization, we're then concerned with, well, are they synchronized in the lab frame or not? It turns out they are synchronized in the lab frame. Why? Because we see that these clocks have a separation that is perpendicular to Carla's motion. So displacing something in the perpendicular direction does not cause any non-trivial transformation of coordinates in relativity. If we look at the Lorentz transformations, here in standard configuration, we have x prime equals gamma x minus vt, and t prime equals gamma t minus v over c squared x, but we just have y prime equals y. So if we look in the direction perpendicular to her motion, it doesn't get transformed at all. And then also these equations don't involve y at all. And so it doesn't matter that the clocks are displaced in the y direction. It doesn't cause any desynchronization. So in part B, the offset between the clocks is just 0. Finally, in part C, we can still just use time dilation. That we know that Carla's clock is running slow by a factor of gamma, so the clock A has to be ahead by a factor of gamma. And at any given moment, the relationship between Carla and the center is the same. It's always displaced perpendicularly. We have a symmetry with respect to rotation angle here. And so it doesn't matter where around the circle she is. This clock always is just running fast by a factor of gamma from Carla's point of view. But things get much trickier when we get to part D. And in order to answer this, we need to think about what are the various reference frames involved, and we need to do a fair bit of math. So when Carla is concerned with what the stopwatch measures when a time tau has passed, we need to think about what is Carla's reference frame and what is the lab reference frame. So we're going to imagine that Carla is right here. She's gone some angle theta around the circle. And we can figure out a formula for theta in terms of tau. That's fairly straightforward, that theta is the distance traveled over r, which is velocity times time that she's been traveling, divided by r, which is velocity times tau times gamma over r. That's just the factor for the time dilation coming in there. So we know where she is, but what we really want is we want to say, here's an event, event 1. Carla's stopwatch reads tau, and we're looking at the position of Carla. And then the question is asking us about, that's event 1. Event 2, that at the same time as that, from Carla's frame, what is the reading on this clock over here, clock B? And so in order to do that, we could start defining some coordinates. So the solutions go through and say, well, let's define a special coordinate system like this, where I believe this is A and this is B in the solutions coordinate system. The reason for doing that is now we have one coordinate system that is in the direction of motion of Carla, so that basically plays the role of X in the standard transformation, and one coordinate which is perpendicular, that plays the role of Y. And we could figure out what are the coordinates A1, B1, T1 in the lab frame. What are the coordinates A1 prime, B1 prime, T1 prime in Carla's frame. And so some of these we know by just looking at the picture. For example, B1 is clearly R, because that's just how far it is. And some of these we figure out by Lorentz transformations. So B plays the role of Y, so B and B prime, those are the same thing, right? So some of these coordinates we can figure out by Lorentz transformations. Some of these coordinates we can figure out by just looking at the picture, or just from the way that the problem is set up. So this time is just gamma tau, for example. And A1 is 0. And A1 prime, I don't remember, but we could just plug in the Lorentz transformations to find that. And if we plug in the Lorentz transformation equations here, what we find is that this is actually gamma squared tau. So that could be a pitfall, is that you might think, well, Carla, her stopwatch reads tau, therefore the time coordinate in her frame should just be tau. That's not true, because Carla hasn't always been in this frame, right? Carla started off in this frame, and then she was in a frame that was moving like this, and then later she's in a frame that's moving like this. Eventually she'll go all the way around, and she's back in the same frame that she started with, but this is the time coordinate in Carla's frame when we do the transformation. And then we need to figure out the coordinates in the lab frame as well. So we have T2, A2, and B2, and T2 prime, A2 prime, and B2 prime. So again, these are related all by Lorentz transformations. And some of the coordinates we can write down by looking at the picture. Some of the coordinates we can write down from Lorentz transformations. Some of the coordinates we can write down from the conditions of the problem. So we want these two events to be simultaneous. We have to be clear about which frame they're simultaneous in. They're simultaneous in Carla's frame, which means that T2 prime equals T1 prime, or gamma squared tau. And then A2 and B2, these are the ones that we can figure out by looking at the picture, that A is minus R sine theta, and that this is r cosine theta. So we don't offhand know, well, we do know B2 prime by Lorentz transformations is the same thing, but it won't really matter. We don't offhand know A2 prime unless we use a Lorentz transformation for it, which is a bit tricky because that involves T2, which we don't know either unless we write a Lorentz transformation for it. So what we really need to do is write a Lorentz transformation equation for T2 and write a Lorentz transformation equation for A2 prime, and then plug this one into there. And then what you wind up getting is you get an equation for T2 in terms of T2, and you have to do a bunch of algebra. If you do all of that, you'll eventually find what I got here is T2 times 1 plus V squared gamma squared over C squared equals gamma to the third tau. Where did it go? Gamma to the third tau minus V gamma squared r sine theta over C squared. That's what I found by doing all of those transformations and starting to solve it, which looks pretty bad until you start to get a sense of, oh, wait a second, this term looks a little bit suspicious to me. I've got a gamma squared here, and I've also got a V squared over C squared that I'm multiplying to it. What if I just work all this out? It turns out that this thing is just gamma squared. And so the whole thing simplifies a lot because this gamma squared can go away with this thing can become gamma to the 1. This gamma squared can go away. And then that's our final answer. So I think that, what was interesting to me about this problem was, one, the fact that we were talking about circles, which you may not be used to, but also that there was a mix of, in some cases, we could answer the problem almost completely intuitively by just saying, oh, well, time dilation comes up, therefore the clock's going to run slow. In other cases, we really had to do a lot of careful algebra before we finally got to what was going on, and had to use the Lorentz transformations pretty carefully. And the solution I presented here is slightly different than the ones in the solutions, so you might want to check them both out. Okay, I don't see open questions on the Q&A thing right now. So given that, I will move on to part B, string cheese. So this problem, spin cycle, that was written by one of our coaches, Abhijit Krishnan, who is just about to graduate from Harvard. So he's not here today, but if you come in a future year, you may be able to meet him. And so the next problem, string cheese, that was written by me. So yeah, I enjoy fluids, and so this is a fluids problem. And it's kind of, the goal here is to let you practice with all of the big results that pop up inside of fluid dynamics on the USAPhO syllabus. So fluid dynamics itself, we definitely don't deal with all the results of fluid dynamics. Fluid dynamics is absolutely huge, but we only deal with a tiny little bit of that inside of the physics course here. But this problem just let us combine all those things into one problem. So here in part A, I don't think I'll talk about it too much. We basically just have uniform acceleration due to gravity. So you're probably familiar with uniform acceleration due to gravity. And so then the question was, can you get the little technical details of the algebra right so that you figure out exactly what the height of the faucet should be? So check out the solutions if you want to work through the algebra on it. In the second part, a tricky thing about this problem is that there's a lot of little caveats going on. And so it starts with saying water is just falling straight down. And then it points out to you, well, that's actually not quite what happens, right? So we know that water can't be falling straight down because if you watch a stream of water and it was falling straight down, it'd be getting faster and faster as it goes further and further down. So if you had a circle, so say there's a stream of water, it's getting faster and faster as it goes straight down. If you draw a sort of a circle cross section here and a circle cross section here, water is going slow higher up and faster further down, which is a problem because if the water is going faster further down and the cross section is the same size, then more water is flowing through further down. And where did that extra water come from? So what actually has to happen is that the stream has to get narrower the further down we go. And if you turn on a faucet and look carefully, you'll see that's actually what happens. And so we need to bring in the continuity equation. So the continuity equation just tells us that the volume of water flowing through each individual part of the stream is the same. In other words, that the volume is the velocity times the cross-sectional area, that is the same anywhere in the stream. So a good technique here would be if you need to choose some particular point to make this V2A2, make that the very top, right? Because the very top, you're given what V0 is, and you're given the cross-sectional area because you know the radius of the stream at the top. So set that equal to your V2A2 here, and then this can be at some other point, arbitrary point in the stream. And then once you've brought in that extra fact, again, it's some algebra. But it brings up another question, which is, well, if the water goes and it gets thinner, look at this little piece of water right here. It moved like this, right? It didn't just move straight down, it moved sideways some as well. So if you look at an actual stream of water coming out of your faucet, it doesn't move sideways very much. It's mostly down with a little bit of sideways. And so here we just ignore the sideways movement. But in the next part of the problem, what we said, okay, sure, we can ignore the sideways movement, but we are going to take account of the surface tension. And so what the surface tension does is it pulls from all sides, pulling in on the stream of water. If you just have a drop of water, so it's not falling or doing anything, just sits there, surface tension pulls in from all sides, and the drop will be under slightly higher pressure than the surrounding atmosphere. That applies just as well in the water. So originally I wrote this and was trying to force you to rederive the Young-Laplace equation. Fortunately, the other coaches talked some sense into me and said, no, that's not actually what you really care about here. What you care about is the stream of water. So what we care about is the stream of water. This effect of this is what surface tension does is something that we're using for it. But the idea is if you have a really tiny stream, a really thin stream, and a really thick stream, which one does surface tension affect more? Surface tension affects the smaller streams more, and the larger things get, the less important surface tension is. So small insects can stand on the surface of water, buoyed up by surface tension. If you took the exact same insect and made it a 10 times scale replica of it and tried to put it on the surface of the water, it would fall through. So doing some sort of like dimensional analysis exercises can lead you to see how length scales come out of surface tensions. Try taking, for example, a density and a surface tension and a gravitational acceleration and a length scale, and see if you can make a dimensionless group out of that. If you can, you should be able to basically solve for a length scale in terms of these other things. And that length scale will be the length scale in which surface tension effects become significantly important in situations where gravity is involved. The number that you get out of this, by the way, is called the bond number. So if you see surface tension problems, a bond number is something that will often pop out of it. So as we go further and further down the stream, the pressure gets higher. So this is high pressure, and this is low pressure, which means if we have a bit of water that's falling down, it is falling down against a pressure gradient. It has a force on it, pushing it back up. So it has a gravitational force pulling it down, and that gravitational force is going to win. But there is a pressure gradient force pushing it back up and slowing its fall. And so we need to account for that. The way that's accounted for is with the Bernoulli equation. So here we just wanted to cite the Bernoulli equation, which I can write as 1/2 rho v squared plus rho gy plus the pressure is a constant. So I'll compare to the original. So this is an equation for energy conservation. We use energy conservation all the way back in part A. We can use energy conservation again here. And each of these terms is basically an energy or an energy per unit volume. So this is a kinetic energy, and this is a potential energy. And the pressure itself is not an energy, but if I take from the two sides, P minus P naught, and then this is all per unit volume. So if I were to multiply that by a volume, a pressure times a volume, that's an energy. So the change in the pressure as you move down tells us basically how much force was pushing this thing back up. If I multiply by the distance across which it traveled, I find that what matters is that the work done on it, this is basically like a work. This is like a work that's done on it as it travels down. And so that work goes into the change in all of these energy terms. And then you can crunch through a bunch of algebra and get a solution for that as well. And so then finally, if you do this with your faucet at home, you'll notice that it doesn't turn into a smoothly falling stream that gets narrower and narrower and narrower. Eventually it breaks up into droplets. And so why does it break up into droplets? Well, the theory is that the shape of the stream, it's almost smooth, but it has little variations and bumps in it as you go. And what we can do is, in general, we can break down a complicated profile like that into sine waves. So we can break it down into something that's varying like this and something that has a higher frequency, et cetera. And by adding up enough of those sine waves, we can get the complicated shape. And what we'd like to do is analyze the sine waves individually. So we're analyzing something like this. And if the sine waves are the right length, we can imagine that what happens is, if I have a stream that looks like this, that these variations get bigger with time. If I have a stream where they're the wrong length, and I start with something like this, then maybe with time, it actually gets smaller. So I still have maybe some variation, but that variation is getting smaller with time. So how does it decide whether the variations are going to get bigger with time or whether the variations are going to get smaller with time? Well, that depends on the pressure. The pressure has to force the water around. So suppose I start with this thing and I have a narrow area, and a little bit beneath it, I have a thick area. If the thick area is going to get bigger with time, that means that water has been forced from the thin area into the thick area. So why is water getting forced from the thin area into the thick area? Evidently, if this is going to happen, then I must have high pressure here and lower pressure here. So you might think, of course, well, obviously, you're going to have higher pressure in the thin areas and lower pressure in the thick areas, because the equation said that the pressure depends on this radius, and the smaller the radius, the higher the pressure. But that's not quite true, because there's also curvature in this direction. And so we need to account for both those sources of curvature. So the solutions will walk you through looking at the curvature along this direction. And if we declare that we want the pressure in the thin region to be greater than the pressure in the thick region, then after some algebra, you again find that it turns out that it is when the wavelength is equal to the circumference of the stream. It turns out that when the wavelength of these variations is equal to the circumference of the stream, that on one side of that, that the perturbations will grow, and on the other side of that, that the perturbations will shrink. And so this describes the dynamics of a stream breaking into droplets, which is an everyday phenomenon, but which you probably have not really considered the physics behind before. So it looks like everybody has been answering the questions as we go along, because I see the number of questions has increased, but there are no open questions at the moment. So I can answer any open questions, or I can turn it off to, I believe next will be Kai.
Yeah.
All right.
All right. So I guess there are no questions for now. So I'm going to move on to B2, which is mirror, mirror on the wall. Oh, there's a quick question for JJ, if you want to take that first.
What is the quick question?
Or actually, it doesn't seem like it's in the about the fluid form. So I think someone can answer it in text, and then I'll work on it on B2 for now.
Okay.
Right. So B2, which is mirror, mirror on the wall, the setup is you have a box, and shoot, I need to share this because I can draw things, but they mean nothing if nobody sees them. Right, so the setup for B2 was you have a box and you have a mirror on the bottom and a little point source. And the question's asking things about basically what are the interference patterns on this wall and what are the interference patterns on this wall and what happens with like extra stuff and so on, right? And I think this problem is relatively straightforward as long as you recognize basically what the problem is really asking, how to simplify the problem into describing this as, you know, when you have a single box, a single point source against a mirror, right? To think of it as simply one point source and another point source, where this one has a plus, you know, 180 degrees or plus pi phase shift because it's in a mirror, and to work with it, you know, as though it were just simply 2 point sources with a phase shift, right? That makes part A much simpler to think about because all you really need to do then is to derive, you know, the usual, or even use what you know already about simple two source interference patterns, and the fact that this one has an extra phase shift just means that you flip all the white peaks with the black peaks. So that's part A. Part B is mostly about error analysis, so I'll get back to that in a little bit. But part C is, you know, we add a little kind of mirror, a little hemispherical, and I know that doesn't look hemispherical at all, shell to this point source. And if you think of it as, you know, point source and a mirror and a shell, that's much more complicated than think of it as simply I have a point source in a mirror. I have a point source and its image in a mirror, and everything coming from this point source goes through the shell, and everything coming from this source doesn't go through the shell. And if you think of it that way, then it's once again just a simple you know, two point source interference pattern where you apply what amounts to an arbitrary phase shift to the first point source. And as long as you know how to calculate the phase shift using, you know, the thickness and the index of refraction of this shell, you're good because it's basically the same problem. And then finally, part D, which is instead of looking at the interference on the right, we're looking at the interference pattern on the top. And again, as long as you look at it as, you know, here's my point source, here's its image, and be able to work out the geometry to derive it correctly, then you can derive the pattern as well. I do want to mention one thing, which is the written up solutions sort of do a thing where you take the, you know, the Cartesian, the x and y coordinates of the say a point on the image, and try to calculate the path distances by doing a Pythagorean theorem, like a square root, I think, like L minus D squared plus X squared versus up here, since this is, you know, an L minus D, and here is an X, and then subtracting that from a, or L plus D squared plus X squared. But I think there's a much more kind of intuitive way to do this geometry, is to basically look at these sources and try to approximate them by simply using the fact that the point sources are really very close to each other relative to the length of the wall, right? So if you were to draw two rays, one from the image in the mirror, one from the actual image, the actual point source to a point on the wall, these lines are mostly parallel, right? And so you can use, and this is true for the usual two source as well, right? I'm sure you've probably seen an expression like this, which is if the angle from the rays to the horizontal is theta, the path difference between the two is the separation. In this case, there's a factor of d here and a d down here, so 2d. That this width, the path difference from the two rays is 2d sine, or yeah, d sine theta, versus up here, because you're moving in the other direction, you could work out the geometry so that if you have this angle and look at if that's theta, then this path difference by some trigonometry is 2d cosine theta. And if you write things in terms of that, I think it comes out to be much more straightforward to do the geometry. So, so those are parts A, C, and D. The part B is mostly about error analysis, and I think that's probably, I think, one of the trickier parts of this problem, which is, you know, how do we choose a D to minimize the actual error in our measurement? And I think the way to go about problems like this, and really this is applicable to doing lab work in general, is that we're really asking, you know, if we have no control over the error in our measurements in sort of the, you know, the minimum tick width of a ruler or how well my hand can be steady, right? We want to design a setup so that our the final result that we calculate is the least susceptible or sensitive to changes in how we measure, right? And so the first thing to do, of course, is to figure out how the result we're calculating, in this case, it was we're trying to measure the wavelength, is related to our inputs, the things we measure, which in this case are the D, the distance of the source from the mirror, and Y10, which is the maximum spacing, the spacing, the position of the 10th fringe, and so on, right? And if you do out some math, right, you pretty much get out, I believe lambda is something like, it was 8/19. This factor doesn't really matter, times, what was it? Let's see. Apologies for the noise. I think it was like a L, nope, the L is on the bottom. Like a Y10 over DL, does that seem right? I think that seems, oh no, that's not even, never mind. The D goes on top and the L goes on the bottom. I think that's reasonable. Someone correct me if I'm wrong, because I am momentarily blanking and I'm too lazy to rederive all of this. But I think this is right. So you get out, you know, you can do out the math and figure out this is the wavelength related to the things we measure, right? And if we do this, then what we figure out is, you know, if we make a measurement, if we measure Y10 and D to be something, then we measure, you know, lambda to be this. And then the question is, if our measurements are inaccurate, if say the actual value of Y10 was supposed to be 1.1 centimeters, but we measured something like 1.12 or 1.06 centimeters, right? If our hands shook or something, or simply we're not very good at reading the tick marks, or the tick marks are just not strong enough, right? How does that change our output, right? And the answer to that is, if you're looking at small variations in the inputs and trying to figure out how that causes the output to vary, right? The standard thing to do is to take a derivative and basically linearly approximate how a small change in the inputs affects the small change in the output, right? And so one way to come up with, because I think the written up solutions don't quite mention how we got to the sort of delta lambda over lambda is equal to square root of, you know, delta D over D squared plus delta Y10 over Y10 squared, right? One way to do that is to just take a derivative and figure out, okay, suppose I have a small change in Y10, right? Then if I were to take a derivative and figure out that, then I say, well, what's the derivative of lambda with respect to Y10? That's 8/19. D over L, right? And so then if there's a small change in Y10, then the small change in lambda is basically, we get out this, right? D over L, which is the derivative, times the small change, right? And the same thing with D. If there was a small change in D, if you took a derivative, then you get out the that the small change in lambda is proportional to the small change in d in the same way. Now, there's one other trick that I want to talk about, I guess, which is when all you have to do is whenever your function is related to the inputs by something like product of powers. So in this case, it's something like 8/19, what looks like d to the 1 and l to the -1, or a product of things like this. Right. One thing you can do is, instead of having to take a derivative for each one of them, right, is to look at it from take a log of the whole thing first, right? And by log, I mean natural log, because I'm a mathematician. But if you took a log of this, then you get log of the constants plus 1 from the power of log d plus -1 times log L, right? And in general, if it were, these were like, x to the a and y to the b and z to the c, right? And you took a log, you would get a log x plus b log y plus c log z, and so on, right? And if you look at this, and then you do the same thing where you take a derivative to figure out, how does a change in the inputs d and l affect the output, right? If you took a derivative of all of these sides, you get out pretty much that a small change in the log of delta over, a small change in delta over lambda, a small change in lambda over lambda is proportional, or is equal to this thing being a constant, doesn't have any changes, is proportional to a change in d by basically in the same way times the constant, which is its power, right? Plus a -1 times a small change in L over L, right? And this is more or less how we got to that. Now, there's one thing you want to be careful about, which is these two, the L and the D, right? These two measurement errors, they're not actually like, function parameters. These two are errors in the random sense, which is there's a random distribution of how my hand shakes or how I like inaccurately read a tick, right? And so this error, instead of adding them and or even subtracting them because of the powers, right? We think of these as, these are the magnitudes of the errors. And statistically, there's a statistical fact, which is if there are two sort of random variables and I add them, the typical variation, what I get from adding two random errors, is the sort of sum of the square, the root sum squares or something like that. And so this is how we got to the delta lambda over lambda is square root delta d over d squared, delta L over L squared. And in general, if we're looking at a function like this, like in a function where we had w is equal to x to the a, y to the b, z to the c, we would get out something like delta w over w. This is being like a percent, a relative error thing, is basically equal to a delta x over x squared plus b delta y over y squared plus c delta y z over z squared, right? So this is like a log trick for figuring out, and you don't have to rederive this because after doing this, you can just figure out, oh, if I look at the powers, then the relative error is proportional, to the powers, pretty much in each direction. So that's all I have basically to say about B2. If there are no questions, I'll hand it off to B3.
Okay, I guess I'll go from here. Hi, everyone. I'm Brian Skinner. I'm going to talk to you about the last problem on the exam, B3. Okay, I think you can see my screen, I hope. Oops, okay, here we go. So this problem is secretly asking you to derive a famous result, which is the van der Waals equation for gases. So you learn, PV equals nRT, the ideal gas law. And this is sort of the first correction when you allow gases to interact with each other. Now, this equation A is actually secretly the van der Waals attraction between gases. It comes from two atoms basically having fluctuations of the electron cloud, and those fluctuations synchronizing with each other and leading to this weak interaction that looks like 1 over r to the 6th. So just for simplicity of the problem, we said, okay, assume it has the attractive part. Usually what you get for the attractive part is that you have what's called the Leonard-Jones potential. It has a repulsive part very close and then an attractive part in the tail. We sort of killed the repulsive part for you to make this simple. But the idea is that the atoms now have a weak attraction. Now someone asked, in the questions at some point, someone asked, well, why doesn't it happen if the atoms attract each other, they all just clump together? And the answer is that we're sort of implicitly assuming that this epsilon is small. And I guess we should have stated that explicitly in the problem. But if this epsilon is small, then it's really just sort of making a weak change to the way the gas behaves. And so we're going to get somehow a correction to the ideal gas law, correction to the way that gases behave. So really you should say that this epsilon should be small. And what should it be small compared to? Well, it should be small compared to the kinetic energy of the gas particles, which is kBt. Okay, so if I assume that this factor epsilon is small compared to kBt, then I can go through and calculate everything the way we said. So the first part, it asks you to calculate the average potential energy of an atom. Okay, so this is really just saying, if you know the attraction energy, then within some differential piece of volume dV, there are, n over v times dV atoms, and then you integrate the potential energy that comes with their interaction over all of the volume. That's this thing here. You have a little volume element dV, which is 4 pi r squared delta r, 4 pi r squared delta dr, and you integrate that and you get this expression right here. It asks you to write it in terms of this A prime, which for mysterious reasons at this point, it has an epsilon and a d cubed, and you'll later see that this simplifies everything really nicely. Okay, so that's part A. Part B is just asking you to notice that the potential energy near the boundary of the box is different than the potential energy in the middle of the box. In the potential in the middle, an atom is surrounded by atoms in all directions, but at the very surface of the box, it's only surrounded by half that many. And because of that, an atom at the surface feels only half as much potential energy, has only half as much potential energy as compared to one in the bulk. And that's going to be crucial for understanding the pressure difference between the surface and the bulk. Okay, so C, it's asking you to figure out what is the pressure at the boundary. And again, we see Bernoulli's law. Bernoulli's law, as Mark mentioned earlier, is really just energy conservation. So here there's this term rho v squared over 2, which is like the kinetic energy density of a fluid element. That's sort of a red herring here because there's no velocity. Everything's stationary inside a box, so you can cancel that. And now you get P plus U equals constant. Well, U is like the internal energy density, how much internal energy the gas particles, the atoms have. And P is the pressure. And you can really think of this constancy of P and U as like, if you imagine taking a volume element and moving it from one place to another, you're going to do work on that volume element that's like pressure that has to do with the pressure pushing on it. And that'll tell you how much the internal energy changes. Okay, so that's that. And using this thing P plus U equals constant, and knowing already that U is smaller on the surface immediately tells you the difference in pressure is different. And if you know that the pressure from the normal gas law is just, N kT over V, then that tells you that the pressure at the surface is smaller by this factor here, A prime N squared over V squared. All right, now part D, what's the total energy? Again, this is pretty simple. You already calculated the potential energy, so now you just have to add the kinetic energy. The kinetic energy looks like 3/2 N kBt. This is what's called the equipartition theorem. Equipartition says that there's in thermal equilibrium, there's 1/2 kT of energy for every degree of freedom. So atoms can move in 3 directions, so they have kinetic energy 3/2 kBt. And that's that. So you're just adding that potential energy to the kinetic energy. Now the last, there's part E. Okay, part E is telling you that the total energy of the gas is conserved, but now you will allow it to expand from a container of volume V to a container of volume 2V. Now the total energy has two parts. It has kinetic energy, it has potential energy. We know that the potential energy is going to decrease if the volume decreases. So now you just have to equate the expression before and after the total energy 3/2 n kVt minus this thing A prime n squared over V. This is the potential energy part. You know the potential energy is going to decrease. So you can figure out from there the change in temperature. And that's this thing. All right, so F is the trickiest part. And it asks you, what is the increase in entropy of the universe as a result of the free expansion? Now, what you're supposed to realize here is that because the total energy of the gas is not changing, that means that there is no energy flowing into or out of the box. So the gas itself is like a closed system that does not communicate with the outside world. So there's no change in anything outside the box. And the question of what's the change in entropy of the universe is the same as saying, what's the change in entropy of the gas? Now, because there's no energy being lost and no energy being exchanged, this is what you call a reversible process. A reversible process in thermodynamics is something where how you get from point A to point B doesn't matter. And all that matters is that you can figure out all properties just by comparing point A and point B. And the path you took to go from A to B doesn't matter. So in this case, we said that, okay, the way it got from being in volume V to being in volume 2V was that you quickly remove some partition. But you can imagine any process you want that went from V to 2V. And the change in entropy associated with that process will be the same as the one that happened in the real process that I told you about. So what you can do in particular is to imagine that you just slowly move the partition, that the problem tells you you quickly removed it. But if you slowly removed it and you calculated the change in entropy associated with that slow moving to move it from a volume V to 2V, the change in entropy you get there will be the same. So this equation here, ds is p dv over t, that's really like p dv is like the work done, and this is the work done by the moving partition, which experiences a pressure P. This equation that looks like work done over T is change in entropy is a standard equation for reversible processes. And since we're thinking about a reversible process, we can use this. And now the only question is, what is P? Well, P is now the pressure at the boundary of the moving partition, because that's what determines the work, is the pressure, is the force that's at the partition. So you can calculate that from what we had before. And now the rest is just sort of, you have this equation, ds is p dv over t, and the rest just comes down to integrating this ds over the change in volume and keeping terms that are only first order in this A prime, which again comes down to assuming that the energy of interaction, this epsilon, is small. So you can keep only our Taylor expansion with the first term in epsilon. And what you get at the end should look nice, because this first thing, delta S, is nk log 2. That's what you'd expect from an ideal gas. That log 2 just comes from the fact that every atom now has 2 times as many locations to be in. So the entropy goes up by a factor of log 2 per atom. And this is now the first correction associated with the interactions. Basically, gas particles have slightly less entropy because they interact with each other. And their interaction means that they're slightly less free, slightly less random than they would have been without the attractive interaction. Okay, so that's about it for that question. Any questions for me? Or any questions about this last problem?
Okay, it seems we have 20 minutes left for the, okay. So Brian, there is some question about this question.
Let's take a look. Why can we assume the entropy change is the same as the partition is removed slowly versus quickly? Okay, so the problem statement tells you that the partition is removed quickly, but it also tells you that no energy is exchanged with the surroundings. It tells you that the total energy of the gas is the same. And if the total energy is the same and there is no interaction with any environment, and then that's sort of what defines a reversible process. A reversible process is one for which no energy is lost. An irreversible process is something where there's some kind of friction involved. But when there's no energy exchange and the gas starts at equilibrium and ends at equilibrium, that's a reversible process. And for a reversible process, it doesn't matter how you got from the initial state to the final state. So we're free to imagine a process where the partition moves slowly. I hope that answered your question.
Yes, and please keep the questions coming. We still have 20 minutes left for this webinar. And before we go into details about further questions that you may have, I just want to thank you again for supporting the US Physics Team program. And I also want to point out that the US Physics Team program, one of the mission is to train and select a team to represent the US to compete at the International Physics Olympiad. But that is not our sole mission. Another very important part of work that we meaning all the coaches and all the folks at American Association of Physics Teachers are trying to do is to build a physics learning community so that we will be able to support your interest in learning physics, and we will be able to distribute the learning materials and resources in an equitable and in a very open way to encourage you and your friends and your younger siblings to keep doing this. So as I was getting a lot of the questions about which textbook to use for USAPhO or for IPHO, my first reaction is always, if doing these problems make you happy, by all means keep doing that. But to study only for IPHO or only for USAPhO problems, then you really don't need anything much beyond HRK, Halliday, Resnick, and Crane, or the mechanics book from Morin, or any good thermophysics book or optics books. Okay, so yeah, and keep having the questions coming. So someone was just asking in the chat box, is Griffiths overkill for USAPhO and ENM? If you only want to study for USAPhO, I think Griffiths is a good resource to study it. In fact, it has a similar problem to the breaking up problem this year. So, but again, only if it makes you happy doing that, rather than feeling like torture going through all these problems.
Yeah, one thing I'd add is that something like Griffiths has a lot of mathematical tools in it. So it goes through a lot of vector calculus and stuff. If you're in high school and you're like, oh, I really want to learn vector calculus, that's great. But you don't have to. You don't have to rush ahead and say, because I'm advanced in physics, I'm going to study the college curriculum with the extra time that I have. You can pursue whatever is the most interesting thing to you. So I'd say, if you're at that point where you have learned the basics of electromagnetism and you have a good understanding of things like flux and changes of flux and induction and things, you could go learn the more mathy version of it, or you could take that time to build your own radio, or to play around with an Arduino, or just find the thing that is the most motivating to you, rather than be like, I have to go on to the thing that's the next higher thing up the ladder.
Along those lines, there's a question about what is a good starting place for learning topics beyond mechanics. Coaches, what's your thoughts? I'll throw this question to Kai, because he's the one with the most recent memory of preparing for the international competition. And what did you start with beyond mechanics?
I feel like maybe a good part of at least my experience for things like electronics and stuff has been kind of, like almost kind of playing with like sort of like circuit kind of things out of interest. So sort of like Mark mentioned, right? Like of course I think a good part of why I do know some more like physics outside of mechanics is that I like had a good physics class and so on. But like other than that, I think in terms of like having the intuitions, sort of having the interest of like trying to think about how does an inductor work, or like how do I kind of expect resistors and capacitors to behave. I had this like sort of digital electronics engineering class in high school, and what we did there was we just like it was for like a part of it was doing kind of robotics things. Part of it was just kind of designing your own little something that's like a motor that like drives around or something. I made a thing that was a motorized kind of attachment to my door, so that when I clapped it, it would like turn a motor to turn my door handle to open the door. And this was because I keep forgetting my keys. So I wanted a way to open my door without needing keys. But like what I did there, right, is in the process of doing these things that are interesting to you, right, you kind of have to be like, well, okay, like how in the world do I hook up this motor to get it to, you know, have enough current or whatever, and then you can like in the process of it like come to get some understanding of like, oh, well, I have to calculate like what is the load on this motor, like how does it behave like a resistor or an inductor, and you do those things, and then you know you Google around, you watch a bunch of YouTube videos, and like one way or another you kind of absorb some information about like you know, these things. And of course you can't do that with every single thing in physics, especially the most modern. Like you can't just out of interest run a special relativity experiment from your backyard. But I think like a good part of it is just sort of being interested and just absorbing information from wherever you find it.
Yeah, premise is being interested. And I also want to mention this year's USAPhO, we didn't have a circuit problem, but in the past we have had some interesting problems about Zener diodes and things. So feel free to dig into it. And if I recall correctly, 2017 has a really nice graphing problem on the Zener diode in a circuit. Yeah, it's a Zener diode problem. So take a look at the 2016 USAPhO problem. It's a pretty nice problem. And along the lines, you know, in doing physics problems, there are certain problem solving techniques you will acquire. Things including drawing the diagrams and figuring out the asymptotic behaviors of these curves. So and also analyzing the extreme cases. So these are some of the good skills that's very useful in speed up your problem solving. Yes, this is maybe someone also asking how to solve problems faster. Any wisdoms from the coaches?
I mean, okay, I was never an Olympic gold medalist, but one thing I can say is that the more physics you know, the more you'll see connections between one field and another, and the more you'll see clever ways around the obvious slow solution. Like when you can make connections between different fields, you can sort of intuit what the answer should be and solve things by analogy. And I guess what I want to say is just learning lots of physics and learning to make connections between different fields will make you faster by itself. Because you'll learn to not do things the obvious slow way. Probably, I don't know, I would guess that Kai at least probably has better tips than that.
So if I can just give an example, if you look back at, so I talked about the relativity problem, and there was one part of this problem where we found the reading on clock A, and then there's another part of the problem where we found the reading on clock B. So if you find the reading on clock B, we recognize that clock A and clock B are in sync with each other whenever the astronaut has gone all the way around a full circle. And in fact, when they go around half a circle as well. So if you do a whole bunch of algebra, you should be looking that that algebra is going to simplify such that when the astronaut happens to have gone all the way around one full circle, then your two answers to those two problems are the same. So you should have some sense of like what the algebra is going to give you as you're doing the algebra. And then that can help you find mistakes as you're going along doing it.
And maybe a related thing that's worth trying to get into the habit of guess what the answer should look like before you derive the answer. Have some feeling of what you think the answer should be or shouldn't be before you actually make a derivation. And then when you get there, you'll have some feeling about mistakes you make along the way or whether it looks like you got to the right place.
Let's quickly go through a couple of these. We're being asked about linear algebra. Linear algebra is great, but I think it's the same story as with, you know, vector calculus or whatever. If that's what you want to learn, then go ahead and do it. But it's not like, you know, you must learn linear algebra right now while you're in high school. Someone was asking about the Gibbs free energy, which is cool. You're going to run into the Gibbs free energy, and then the next year you'll have the Helmholtz free energy, and the next thing you'll have the enthalpy, and then the next thing you'll have this or that. It's all the same idea, which is that it's all just the universe trying to maximize entropy. But we usually don't think about the entire universe. We try to think about one subsystem at a time. So it's just a way of making sure that we're maximizing entropy for the entire universe while focusing on one subsystem at a time. HRK is textbook physics by Halliday, Resnick, and Crane. there are actually two Halliday and Resnick textbooks. So there's one called Fundamentals of Physics by Halliday, Resnick, and Walker. There's one called Physics by Halliday, Resnick, and Crane. They're both pretty good. The one by Halliday, Resnick, and Crane, though, has more problems and somewhat more interesting problems. The current editor of that textbook is Paul Stanley, who was the academic director of this program before Jaja. And so he put a lot of good stuff into there. So I generally recommend Halliday, Resnick, and Crane over Halliday, Resnick, and Walker.
And since we got all of your attention here, perhaps it's a good way to turn the table around to you. And if you can perhaps type in into the chat box and let us know, what are the various ways you have been utilizing to study physics? Do you have study groups, and do you have sort of friends and pals or siblings to work with you? Or are you just banging your head against a textbook over and over? I'm just curious to know. And yes, another question from the chat box is, when this is recorded, will all of the links be shared? The answer is yes. There will be what do you call it? Closed caption, the script transcribed along with the video as well. Yeah, and a lot of people were also mentioning, is it important to do a large number of problems? It is really important to do rather a finite number, a small number of problems, but get to the point and get every step of the problem really clear, rather than just sheer volume. It's about efficiency. And of course, you want to have a few problems under your belt. So like Brian was saying, if you've seen a few of them, then you will have a better intuition and have a good guess on how these things are, how the answer should look like. Mm-hmm.
Okay, I didn't know about this Physics Olympiad Discord, so that's really great that you have a place to go and talk about problems with people. So I encourage you to find places where you can go talk about problems with people, for sure.
And now that you are in this community, you know all the coaches, well, at least virtually, and you know where to find us through AAPT. Then what we hope is, you know, there is a group of students who are just like you, maybe in somewhere in this country, and trying to learn physics. So have a group. It makes things a little bit easier, a little bit more interesting. Yeah, I have never heard of this physics Discord either, so looks good. Let us know if you need any additional help to start a physics circle locally, or start from a physics learning community. And that's why we're here, and that's what we try to do. And one thing, it is not quite official yet, because many of you know this, typically we will have a summer training camp for 10 days when we will select typically 20 USAPhO top scorers to the training camp. We're not doing this summer. However, by doing this webinar today, we're also trying to test out the technical platform to do a virtual session like this, and how things are going with you in this medium. So if things go well, and if we rely on a lot of goodwill from the coaches volunteering their time and energy, but if assuming all of these answers is yes, then we will try to host some summer virtual sessions come in June and July, a few times sprinkled in the summer, to make your summertime go by a little bit more physical. So, but this has not been finalized, and we would like your feedback about the webinar, how things are going today, and what your interest level is. So let us know. All right, I'm just cognizant about the time. We have about 5 minutes left. Thank you very much for coming, and encourage your friends to study physics and pick up a book. And the summer seemed to be not much outdoor going on, so maybe this is a good chance to do a few more physics problems. Thank you all the panelists. today with us, and thank you all for coming. You will get an email from Janet about how to access the recording afterwards. Okay? Hope to see some of you next year in person.
All right. Bye, everyone. Thanks for coming.